Okay, recording has begun. We will, let's just wait another minute or so, see if anyone else joins in, and then we will get started in just a second. Oh, thank you. Yep. If you guys could just drop your, I would say, email in the chat so I can record attendance later, that would be great. Oops. Okay, so welcome back, folks. We will go ahead and get started. It's 4:30. So like I see a lot of you guys are doing, if you could just put your Iowa State net ID in the chat so that I can record attendance, that'd be awesome. So today we're going to continue on chapter 3. So your chapter 3 exam and quiz and everything is this, I believe it's due this Friday. So today we're going to continue on chapter 3 and talk a little bit about different types of reactions, percent yield again, and then limiting reactants. And then tomorrow, I figured tomorrow we can, since we've pretty much covered everything so far for chapter 3, we can talk about if there's anything you guys want that I didn't cover. Otherwise, tomorrow's session at 4:10 will be like a review. So we'll take all the stuff we've been doing for the past 2 weeks and we'll kind of like synthesize it into a 50-minute session. And if you guys have any other questions before you take your exams, feel free to bring them tomorrow or send me a message and maybe I can prepare a question regarding that topic for tomorrow. So before we get started, what questions do you guys have for me? Okay, well, in that case, let's get started. Now, I thought what we would do to start today is we would do a little discussion on different types of reactions. Now, I think this may have escaped me. I may have just forgot to do this earlier, but I wanted to get this in front of you so you knew what these different terms mean. So like combination, decomposition, single displacement, and so on. So I'm just gonna write down the form for these reactions, and whenever you see these reactions are always going to be in the same form. So for example, a combination reaction would be some chemical A plus some chemical B goes to AB. They're combined in one. So so the A and B could be, they could be anything, right? So two elements or two compounds or whatever. Idea is you're taking two and you're making them into one. It's a pretty self-explanatory combination. Decomposition reaction, on the other hand, is just combination in reverse. So AB goes to A plus B. So we are decomposing this into simpler pieces. And again, A and B can be, whatever chemicals. And you could even have like more. You could have A, B, and C breaking down. So again, decomposition, pretty self-explanatory. A single displacement is where you would have first chemical A plus BC, some compound BC, goes to AC plus B. So it's called single displacement because the A is replacing the B. It's like kicking B out of its place, and then the B goes by itself. So again, this could be any sort of reaction, but you're displacing a single chemical. So A plus BC goes to AC plus B, and that's the general form. So then a double replacement would be something like AB plus BC, plus CD, and we're doing a double displacement. So this would go to AD plus BC. So the A, I like to call this one swapping partners. So the A is partnered with B, and then it's swapping partners and getting partnered up with C. So technically this reaction is called a metathesis reaction, but it's also called double displacement, or I like to call swapping partners. Another one you're going to deal with is combustion, or complete and incomplete combustion. So if you remember this from the other day, that's great. So we'll go over these once again so we have them all together. So some sort of a fuel, which would be like, I don't know, a carbon hydrogen fuel like gasoline or propane or something. And you're mixing it with oxygen. And this is going to form carbon dioxide and water vapor, H2O. And then it's always going to be the same. The only thing that's different is some sort of different fuel, but it's always going to mix with oxygen and produce CO2 and H2O. Now, incomplete combustion would be some sort of fuel plus O2 still, but the incomplete combustion is in a case when there's insufficient oxygen present. And in that case, we produce carbon monoxide. So notice here, the carbon monoxide, it does not have a 2 here. It's just CO. So these are the 6 reactions that you should be responsible for knowing at this point so far in the class. We're going to talk about acid-base reactions, but those we'll get to in the next chapter. So if someone said, for example, propane or whatever, and they would tell you what propane is, underwent combustion, you would have to know, okay, I'm going to use equation 5 because that's a complete combustion. And if it doesn't say complete or incomplete, you can assume that it's a complete combustion reaction. If they gave you a problem where it says, such and such undergoes decomposition, then you'd have to know, okay, well, I kind of know the basic formula for this. I can probably get the chemical reaction. What questions do you have on these 6 type of reactions?
For the double displacement reaction, can it be A and C and B and D, or is it only A and D and B and C?
It could be A and C, as long as you're like swapping partners. So like the B could go with the D, and that would be completely fine, Sarah. Yeah, these ones, it'll usually tell you sort of like what the products are. And another thing to bring up is that if these are ionic compounds. So this is really important. I want to try to zoom in here. So what Sarah was mentioning is, could A go with C? If A has a positive charge and B has a minus, and C has a positive and D has a minus, the positive and negatives always pair up. So in this case, A would be positive and D is negative, and C is positive and B is negative. So opposite charges will attract each other. So in this case, A and C could not go together because it would be plus and plus go together, and that doesn't work. It has to be a cation, which is a plus charge, with an anion, which is a negative charge. Does that make sense, Sarah?
Yeah, thank you.
Okay, great. Yeah, that was a really good question. So why don't we move on and do a problem here, which is, it's regarding a chemical reaction, and it has to do with a percent yield. So because we did one of these yesterday, what I want to do is give you some time to try to work on this on your own, and then we will come back together and work on this together. One thing, I'll just write down the equation for percent yield in case you forgot. So percent yield is equal to the actual yield divided by the theoretical yield. This is also called the calculated. So the theoretical, also called the calculated yield, times 100. So I'll give you a couple minutes. Try to think about how you would go about this, and then let me know when you have questions, and we'll come back together in a few minutes. Okay, so maybe you've had a couple minutes to look at this. Let's talk about this one together. So you have this process here, and it gives you the chemical reaction. And then it says the factory wants to collect 250 grams of phosphoric acid. So how much diphosphorus pentoxide must be reacted to produce this? So we want 250 grams of this one. Our question is, how much of this one here do we need to add to the water to produce 250 grams? Now this 250 grams, this is what we want to collect, but our process isn't perfect. Our process has an efficiency or a percent yield of 85%. So this here, this 250 grams, this is the actual yield. This is what we actually want to collect. And we also know the percent of how efficient our process is. So what we want to do is we want to find the theoretical amount that is produced. And then once we have this theoretical amount, we can use stoichiometry to go back and see how much of this P2O5 we need to add to the water to make our reaction happen. So we have percent and we have actual. We want theoretical. So we can do algebra and multiply both sides by the theoretical yield and divide by the percent sign. So this might be a little rusty for you if you haven't taken algebra in a while, but these two in algebra, you can swap these two. If one's on the bottom and one's on the top on the other side, they can be swapped. So the theoretical amount is equal to the actual divided by the percent yield times 100. Now, if this is mysterious, how did I get this theoretical and the percent swapped? Feel free to let me know, and maybe we can talk about how this works in algebra. I know it's always confusing for me, but it's one of those things that you just have to practice a while swapping on algebra terms. So let's calculate our theoretical. Our theoretical amount of H3PO4 that is produced. So we have our actual yield is 250 grams divided by our percent yield, which is 85.0, times 100. Clear this up. This is 85% down here. And this will give us a theoretical yield of, let me see here, I got it written down. A theoretical yield of 294.12 grams.
Why did you not do the stoichiometry?
Okay, so is that Ben? Yeah. So Ben asked, why don't we do stoichiometry? We're gonna do stoichiometry. What we're doing here is figuring out just the H3PO4. You only need to do stoichiometry when you go from one chemical to another. So we're just about to go to P2O5, and then we'll do stoichiometry. Does that make sense, Ben? Or did I lose you?
Kind of lost me.
Okay, all right. So let's. My internet's. Let's Can you guys still hear me? Oh, okay. Let's keep going and let me know if you're following, Ben, or if I kept losing you. So we have now what we have is we have right here this H3PO4. This is 294.12 grams. This is what is the theoretical amount that we could collect from this process. And we want to use stoichiometry now to see how much P2O5 do we need to mix with the water to produce 294 grams.
Okay.
So here, what we're going to do is start our stoichiometry bar. So we have 294 grams of H3PO4. Okay, and we want to change this to moles. So 1 mole, we'll put mole on top, H3PO4. And on the bottom, we want to put grams of H3PO4. So how many grams are there in 1 mole? Well, this is where we use the molar mass from the periodic table. And if you go through and get the molar mass, that will come out to 98.0 grams of H3PO4 per mole. Now, if you can't figure out how to get the 98, let me know, and I can run through that again with you. So now we have moles of H3PO4, but we don't want moles of H3PO4. We want moles of P2O5. So I'm going to put this one on bottom because it was on top. It's on top over here, so it goes on bottom here. And put what we're desiring on top. So the P2O5. So moles H3PO4 to moles P2O5. What is the conversion between these two? Who can tell me where we get these numbers right here?
From the coefficient.
Okay, so coefficients. So Ben, would it be just 1, 1, and 1 here?
No.
Why not?
It's not balanced.
Okay, there you go. Yep. So to do stoichiometry, we have to balance the equation. Now, I promise you, if you forget to balance the equation, you're going to get this problem wrong, and all of the problems with stoichiometry. So when you balance this equation, let's see, we have 2 phosphoruses on the left, so we need 2 on the right. So I'll put a 2 in front of this one. So now we have 2 phosphoruses, but now we have 2 times 3 is 6 hydrogens here. So I need to put 3 over here. So this would be a balanced equation. We are just accounting for the number of phosphorus, oxygen, and hydrogen on the left. Has to be the same as what's on the right. So now we have our ratio. And to continue on with what we were doing down here, we have 2 moles of H3PO4 to 1 mole of P2O5. We're just getting the numbers right here and right here. So 2-to-1 ratio. Okay, and then lastly, we are going to go from moles of P2O5 to grams of P2O5. So put moles on bottom so that it cancels with the one on top. And grams of P2O5 on top. And once again, whenever you're converting moles to grams, we're going to use the molar mass. So the molar mass of P2O5 is 141.94 grams. And moles P2O5 is canceling top and bottom. And now you just need to do your calculation. So once again, multiply the numbers across this top and divide the numbers across the bottom. And you should get with 3 sig figs, the answer is 213 grams of P2O5. And that would be your final answer.
How do we know how many significant figures to use?
Great question. So Rose asked, how many sig figs, significant figures do we need to use in the final answer? So the answer is you have to look at the original problem statement. So right here, we're given 2 numbers. We have 250 grams and 85.0%. We have to look at how many sig figs are in these ones. Well, this one had 4 sig figs. 1, 2, 3, 4. And 85% has 3 sig figs. So 8, 5, and 0. So you choose whichever one has the lowest sig figs in the original problem. So we have 4 and 3. 3 is the lowest. Therefore, our final answer has to also have 3 sig figs. Does that answer your question, Rose?
Yes, thank you.
Okay, yeah, good question. I'm not sure how strict they are on sig figs. I've never,
So
I guess my teachers haven't been that strict, but I don't know how it is this semester.
So in order to start the stoichiometry, you have to find the theoretical percent or yield.
Yes, yep. You always, to do stoichiometry calculations, you have to do it in theoretical because that is the calculated amount. You have to do all your calculations in the theoretical. Yes. Okay. Oh yeah, sorry, go ahead.
When we did the first problem yesterday, or
Yep.
whatever day, we balanced the equation first and then did the stoichiometry to find the theoretical and then plugged that in.
Yes.
How are the two problems like different?
So this problem is what we were doing yesterday in reverse. So yesterday I said, find the percent yield. This time I said, here's the percent yield, find the original amount. Now, as far as balancing the equation goes, a good rule of thumb is always balance the equation. Anytime you have to do stoichiometry, you're going to have to balance it anyways. So it's good habit to balance it at the beginning, and I should have done that, Kristen. Should have balanced it first. Does that answer your question?
Yeah, it does. Thank you.
Okay. All right, so we're going to move on. If you still have questions, feel free to ask me once we get the second one started. And I'll try to leave it up here so you can kind of still see. Number 2 says, the following is a step in a commercial process of converting ammonia to nitric acid. And the equation is balanced already for you. In this experiment, 12.5 grams of ammonia reacts with 15.5 grams of oxygen. And the question is asking, how many grams of water is produced? Which is the limiting reactant? And how much excess reactant remains? So we haven't spoken about excess reactants, but essentially limiting reactants and excess reactants are opposites. So the limiting reactant is the chemical that's going to run out in the chemical process. We're going to run out of something, and then there's going to be something left over. If you were here Monday, we talked about making sandwiches. So like we used all of the hams. So the ham would be the limiting reactant, and then we had extra bread left over. That would be like the excess reactant. We have extra bread. So why don't you guys take some time and try to work through at least A and B. And if you want to give it a shot, you can try to work for part C. And let me know when you have questions.
Okay, can I ask like a really dumb kind of unrelated question quick?
Yeah, yep, go ahead.
Okay, so in like an equation like is like the
Yep.
one right under 2,
Yep,
say like with the first 4 NH3,
yes,
so the 4 is the amount is like in moles, right?
yes, yep.
Is the 3 also in moles?
So the 3 represents like the 3 in NH3 here.
Yeah.
That represents how many atoms of hydrogen there are per molecule of NH3. So you could think of it as like every mole of NH3, there are 3 moles of hydrogen. But usually the way people think about it is you have NH3, there's 1 nitrogen and 3 hydrogen molecules or atoms in that NH3. As far as this, you really don't need to think about the number here only when you're getting molar mass. So in this
Okay.
case, I don't know if am I overcomplicating or did I answer your question?
Yeah, I think I understand now. Thank you.
Okay. Okay, so we've had a few minutes to work on this. Let's go through this together. Now, before we start, I want to go.
Before you start.
Yeah, go ahead, Ben.
So like when you're using like O2, when you start with it, obviously you have 15.5 grams. Since
Yep.
it's O2, when you divide by the molar mass, it'd be double its molar mass, right?
Yes, it was. So what would that be?
32. Okay.
Yes. Yep. So let's go through real quick how you would get the molar mass again for different compounds in case people forgot. So let's do NH3. So what you want to do for this one is go to the periodic table and you need to find N for nitrogen. So nitrogen is right here. It's 14.01. So that would be 14.01. Oops, 14, that's a 0.1 there. 0.1 times 1. And the 1 is because there's 1 nitrogen here. And then we have to add on the hydrogens. So the periodic table, the hydrogens are top left, it is 1.01. So we're going to add 1.01 times 3. So there's 3 hydrogens. So 14 times 1 plus 1 times 3. And this will give you 17.04 grams per mole. So for the oxygen, same thing. We're going to run over to the periodic table. Oxygen is on the right over here. It is, depending on the periodic table, it's about 16.0. It's really close. So this would be 16.0 times 2, because there's 2 oxygens in O2. And this would give us 32.0 grams per mole. And then I think the last one we need, oh yeah, we want to figure out how much water there is. So H2O, this would be the same thing. So it's 16.0 times 1 for oxygen, and then 2 times 1.01 for hydrogen. It's the same process, just looking at the periodic table. And this is 18.02 grams per mole. Depending on how you like to go about it, sometimes it's easier just to tabulate all of the molar masses at the beginning, and then you can use them in your calculation. So part A says, how many grams of H2O is produced? Now, in this one, we are given 2 amounts of a substance. We are given 12.5 grams of NH3 and 15 grams of oxygen. My question to you is, which one of these do we use for our calculation?
You have to use them both.
Okay, why do you have to use them both, Ben?
That's how you find which one is limiting.
Okay, so yeah, there's different ways to do these limiting reactant problems, but the way I learned and the way I think is I think is the best way is just to do two calculations. And what we're going to do is we're going to take 12.5 grams of NH3, and we are going to do our stoichiometry calculation and get to H2O, which is what we're looking for. And then we're going to do another calculation, but with the 15.5 grams of O2. And we're going to do the same thing and calculate what H2O is. Now, a word of warning, part B here says which is the limiting reactant. They will not tell you that it's a limiting reactant problem on the exam. They will expect you to know that it's a limiting reactant problem. So another question is, does anyone know, how do you know this is a limiting reactant problem?
Is it like if they give you two values?
Yes, so Sarah said it's because they give you two values. So right here in the beginning, we have 12.5 grams of nitrogen or ammonia and 15 grams of oxygen. That is the telltale sign. Anytime they give you two amounts of reactants, you know it's a limiting reactant problem. Therefore, you have to do two calculations. Just be careful because they will not tell you this on the exam. And the wrong answer will be waiting for you on the multiple choice. Okay, so let's do these ones together. So let's start with the NH3. So we want to get rid of grams of NH3. So we'll put that on the bottom. And we want to go to moles, so we'll put moles NH3 on top. Now, what is the conversion between moles and grams? Well, we just calculated it right over here. For NH3, it's 17.04. 17.04 grams per 1 mole. Okay, so now we're going to go, we want to get rid of moles of NH3. So this one's on top, so we're putting it on bottom here. Mole NH3 down here. And we want to put moles of water on top because that's what we want to get to. So the conversion between NH3 and H2O moles, that is given at the beginning here. So 4 NH3s and 6 waters. So this is 4 here and 6 here. And then lastly, to get to grams, so we have moles on top here. So we want to put moles of water on the bottom. And then grams of water on top. And what's the conversion between grams and moles here? Well, once again, we just found it up here. It was 18.02. 18.02 grams. And this one, let's see, H2O is produced. And I forgot to calculate the answer. I got all written down. Does anyone happen to do this calculation?
I got 10.47.
I didn't quite hear that. Did you?
Oh, I got 10.47.
10.47. Okay. I got slightly different. I got 19.8. Did anyone get
as well?
19.8?
Yes.
I did as well.
Okay. So we'll go with 19.8 grams of water here.
I think the 10.47 was for oxygen.
10.4.
Yeah, it's my bad.
Oh, okay, great. So let's run through and do the oxygen quick. So same thing, grams is here, so put grams on bottom. And moles O2 here. So this would be 1 mole is 32 grams. So again, we calculated that up here. And then again, put mole O2 on the bottom, because it was on top here, and mole H2O on top here, because that was what we want to go to. So the conversion here would be 5 to 6. So 5 O2s to 6 mole H2O. And then lastly, put mole H2O on bottom so that it cancels with the one on top. And 18.02 grams here. And so this one is what did you guys say you were getting? 10 something?
10.5.
10.5 grams.
Do you have to convert it to grams to find the limiting reactant, or can you just do it to moles? 'Cause that's what I did.
Okay, yeah, so you can do that, Ryan. So why don't you explain, Ryan, how did you get the limiting reactant, and then how did you get your final answer?
I just didn't do the last step that you did, which is converting it to grams, and then I saw that oxygen still had less moles than what was the other one? Than NH3 produced, and then I just converted it to grams after I figured out which one was a limiting reactant.
Okay, and did you get 10.5 as well?
Oh yeah, I did.
Okay, great. So Ryan just explained a completely, well, not completely different, alternative way to solve the limiting reactant problems, and his method is completely valid as well. Now, if you watch videos online, or if you learn something from a friend, there are plenty of ways to do these limiting reactant problems, and I encourage you to choose a method that makes sense for you. So Ryan, if that makes more sense to you, then just stick with that, and you will get the right answer. Okay, so then lastly, the question is, which of these is right? This would be the 10.5. So we want to choose the lower amount that is produced. Move this down.
That's the limiting, but not the how many grams, right?
This is the amount of grams that is produced. To find the limiting, what we do is take the lower amount and we track back. We're coming back to the beginning here, and we started with O2. And since O2 is what we started with this in this stoichiometry, the O2 is the limiting reactant. Now, the reason I like this method is because you get the answer and the limiting reactant at the same time. So again, you still have to do 2 calculations, and then when you get your 2 answers, the correct answer is the one that is lower. That's the lower amount is the amount that we can actually produce. And then to get the limiting reactant, trace back the stoichiometry bar to where we started. We started with O2 here, so O2 is the limiting reactant. Before we get to part C, what questions do you have so far? Okay, so let's do part C. Now part C says, what is the excess reactant? So if O2 is the limiting reactant, that means that NH3 has to be the excess reactant. So they're always opposites of one another. So in this process, the oxygen is going to run out first, and then there's going to be some NH3 that is left over at the end. We call that the excess reactant. Now the question is, how much NH3 is left over at the end? Now to do this, what we want to do is we want to take the limiting reactant, which would be the oxygen right here at the beginning, 15.5 grams, and we want to convert this, so convert oxygen to an equivalent amount of NH3 that would be needed to complete the chemical reaction. And this will tell us how much NH3 we actually used during the process. So let's take our 15 grams. I'm trying to leave that there.
So are we using this to solve for A?
We're using this to solve for part C. So right here, this 10 grams, this is the answer to A, right here. This is the answer to part B. And now we're going to work on part C. Thank you for keeping me on track. Okay. So let's take our 15.5 grams of O2 because that was the amount of limiting reactant. And we are going to convert this to moles. So put grams of O2 on bottom, moles of O2 on top. So 1 mole of O2 is 32.0 grams of O2. Okay, so now we have moles of O2. We want to put that on bottom so that it cancels, mole O2, and moles on top. So what do we want to go to? Well, we want to go to NH3 because that is the excess reactant. The reason we're going to the excess is we're saying how much grams of NH3 would be needed to react with 15 grams of oxygen. What is the equivalent amount in grams? So these moles here, this would be from the balanced equation. So it looks like 4 NH3s to 5 O2s. So 4 to 5 here. And then lastly, to go to grams, NH3 here, moles to grams, NH3. And this will be 1 mole is 17.04 grams. Now, if you do this calculation, let's see what we get. We get that there was 6.603 grams of NH3 if you run this calculation. Now, who can tell me what does this number mean? What does this 6.6 grams of NH3, what does this mean?
Is that how much it was used?
Yes, that's right. So this is the amount that is used. Mess that up. We have 6.6 grams is used in the reaction. So how could we find out, Rose, how could we find out how much is left over?
Maybe just subtract it from what we had.
Yeah, right. So we were given 12.5 grams and we used 6.6. So 12.5 grams was given. Let me write that here. 12.5 grams is given. So therefore, the excess NH3 is going to be equal to 12.5 grams minus 6.603 grams. And this is going to be, let's see here, oops, minus with 3 sig figs, 5.90 grams. NH3 is excess. And this is your answer for part C. Okay, we are arrived just on time for the end of the session. Before we end, what questions do you have over this limiting reactant, excess reactant problem? Okay, so we will stop here. Tomorrow at 4:10, we're going to review chapter 3. If you have any requests for problems, feel free to put them in the chat right now. Or if you have any other questions, feel free to stick around for a few minutes. Otherwise, we'll see you guys tomorrow.
I have a question for the excess
Yep.
part.
Go ahead.
I still did it with like the moles, so I converted the amount of moles for the NH3 and O2.
Yep.
And I subtracted the amount of moles of wait, what was the resultant? Can you go up a little? Yeah, thanks. So it was the so subtracted the amount of H2O moles that you got from both the reactants, and then I converted that into grams. I think I got something different.
So you
Maybe I just did my process wrong or something, but I just didn't get what you got. I'll check and see.
okay, you should be able to, Ryan, if you're doing everything in moles, you can do that. And then at the very end, then you go to grams. You just want to make sure what you're not doing. Let's see if you get this. So what you want to make sure what you're not doing is you're not finding moles of water and moles of NH3 and then subtracting those. You can't subtract moles of different compounds. They have to be all moles of the same compound.
Okay. So I'll just do it the way you did. So the way you did it, you took the grams of oxygen. And you converted it to
So we
I
took
don't know. Yeah.
we took grams of oxygen and we converted it to grams of NH3. And that would tell us how many grams of NH3 we used in this reaction.
Oh, okay, yeah. I think I'll just do it that way because that makes more sense. I just did it a different way and probably didn't get it right.
Okay.
Yeah.
Great. Hope that clears things up a little bit for you.
Yeah. Okay, thank you.
Yep, you're welcome.
Okay, goodbye.
Will you record tomorrow's session as well?
Yes, I can try to do that. I will set a reminder and I will try to not forget, Sarah. And
Okay.
then if you want to put, I don't know if you put your email in the chat. If you want to type your email in the chat, I'll try to remember to, oh, there we go. Okay. I will take that and I'll set a reminder to send you an email when I got it uploaded. Does that sound okay?
Thank you so much.
Okay. See you, Sarah.
Bye.